Hello, we're back once again. Whew. So, last time I said that I wanted to finally do this puzzle of Rat Run of Sudoku time with Eve. There is no name for this series. Okay, I give up. And today I think I'm gonna try it out. If you're watching this video, it's because I solved it. If you're not, then I didn't, and I'll try it out again in the future. Hopefully, I'll actually beat this. So, let's do this. This is Rat Run 8 Discontinuous. So this is from the first series. This was released like 3 months ago, but the problem is that I was scared, because this is a 4-star puzzle. I haven't solved many 4-star puzzles. But I want to, so let's try it out. Okay, so normal Sudoku rules apply. Place digits 1 to 9 in every row, every column, in every 3x3 box. And it says here mark with dotted lines. So in these Rat Run puzzles, because there's so many walls everywhere, sometimes it's hard to see the 3x3 boxes, but you know, they are the normal 3x3 boxes of any Sudoku. So they're these areas. Okay. And now, aim of the experiment. Thinks the rat must reach the cupcake by finding a path through the maze. The path must not visit any cell more than once, cross itself, or pass through any thick maze walls. As well as moving orthogonally, Finks may move diagonally if there's a 2x2 space in which to do so, but may never pass diagonally through a round wall spot on the corner of a cell. So what that means is we're gonna have to find a we're gonna have to find a path for Finks to get to, you know, from where she is to this cupcake right here. And the path might be like super long, right? It might go over here, it might tangle around a bit, it might do, whoops, it won't do that. It can't cross walls. It can do that. It can go diagonally, like we said, if there's space in which to do so. But what it couldn't do is that, because that would be passing through a rounded wall spot. That is not allowed by the puzzle. Modifier. Let me just make sure I didn't skip anything. Yeah. There are 9 doubler cells to be located in the maze. So this is probably the reason why it's 4 stars, because these like value change ideas, they don't normally appear in 1 to 3 star puzzles. But here we have, there are 9 doubler cells to be located in the maze, 1 for each row, column, and box, and each containing a different digit. The real value of a doubler cell is calculated by doubling the digit that appears in it. So, somewhere in the maze, you can think of the doubler cells as kind of another set of quote-unquote digits. So, for example, if we had a doubler cell here, whoops, that's not what I meant to do. If we had a doubler cell here, then none of these could be a doubler because they're in the same box. None of these could be a doubler because they're in the same row. And none of these could be a doubler because they're in the same column. So for example, in this box, the doubler would be somewhere in there. And now if it's there, then all these cells are then cleared. So they're kind of a Sudoku set. And not only that, but they all have to have different digits. So if this was a 1, that couldn't be a 1, for example. And indeed, if this was a 1, its actual value for math purposes, which is what we'll get to in a second here, would be 2. And then this couldn't be a 1, but it could be a 2, whose value is actually 4, and so on. And there will be 1 of each doubler cell with each digit. Black currents. The values of cells connected by a black current are in a 1 to 2 ratio. One is double the other. Not all possible black currents have been given. So, for example, these, they could be something like a 1-2 pair. But what they also could be is something like a... Let me think about this. Well... Okay, there's something interesting actually going on with the doubler cells and the black currents, because I'm trying to think of an example. Yeah, okay. yeah, these are going to be interesting. But for example, you could have 1 there and a 4 there, but that could be a doubler. So it's actual values too. So this does work in that sense. Those are going to be interesting in a second, and I'm going to think about them more as we start the puzzle, but for now, let me just keep talking about the rules. Forbidden doors. The values of cells connected by a red X sum to 10. Finks may never pass through a red X. Not all possible red X's have been given. So those 2 cells, first of all, Finks couldn't do a path like that. That's not allowed. You can't pass through a red X. And they have to sum to 10. So they could be something like a 3-7 pair. But they could also be something like a double 3, which is actually value 6, and a 4. That would also work. And finally, test constraint. In this experiment, dotted box borders divide the correct path into segments, each of which must be a valid Nabner line. No 2 cells anywhere on a path segment can have a consecutive or equal values. E.g., if a path segment contains an 8, there may not be a 7, a 9, or double 4 anywhere else on that segment. So that's a pretty good explanation. Basically, if we had something like that, and that was a 1, none of these could have a value of 1 or a value of 2. So, for example, that could be, let's say it's a double 3. Now the values on this line are 1 and 6. So these aren't allowed to have a value of 1, 2, 5, 6, or 7. So this could be, I don't know, a 9. And now that can't have a value of 8 either. So this could be a normal 4. And that would actually be fine. That would be a valid Nabner line there. Because we have the values 1, 4, 6, and 9. None of those are consecutive. And that is the rules, unfortunately. And I say unfortunately because, yeah, this is gonna be hard. I can tell already. But let's have a go at it. So, well, okay, let me just talk about Nabner lines for a second. So usually, when you're talking about Nabner lines, if you think about it, what is the maximum length that a Nabner line could be? And I'm going to claim that usually, without the idea of doubler cells, that max length is 5. Let me see if I can find an example here. Okay, so this is not the correct path because we passed through an X. But let's say this was the path in this box, and there's no doubler cells in it. Well, what happens if we put a 1 there? Well, now the line can't have a 2. So what's the minimum digit we can put here? It's a 3. Now the line can't have a 4, so the minimum digit we can put is a 5. Now it can't have a 6, so the minimum is a 7. Now it can't have an 8, so it would be a 9, and that's it. It can't have any more. Like, if the line continued here, this couldn't be anything. Because it would have to be an even digit, because these are all odd, and all even digits are adjacent to an odd digit. So usually, the maximum number of cells you can have on a Nabner line segment is 5. I'm going to claim that because of the doubler cells, that number is now 6. So I'm going to say that no segment in this puzzle can have more than 6 cells. Because what you can have now is that same arrangement that I said, but then this could be a doubled 8. And that's a 16. That's not adjacent to any of these. But now, if you try to go here, that can't be doubled. So then we're back to the idea of you can't put anything on it. So the maximum number of cells on... That's good, actually, yeah. The maximum number of cells on a path segment is 6. Well, first of all, we're here. We're closed in this little box here. So Finks is going to have to exit it, either like that or like that. Either way, we know she's going to exit it. We know she's then going to follow the path down. And now, does she follow the path right or left? And I'm going to claim that it's not right, because if it was, we would go here, we can't go through the red X, so we'd have to go up, we'd have to go up again, we have to go right, and we have 7 cells in this segment already. And as we said, that's not possible. So we don't go right here. We go left. And then we have to go left again. If we went left one more time, we'd be cul-de-sac. That's not right. So we go down, and that gives us a huge amount of path. And now here we don't know where we go, so we have to stop here. But something cool is that, look at this. This is exactly that arrangement that I said. We have 6 cells there. Which I think means that, first of all, there has to be a doubler there. Because if there wasn't, then, like I said, the max would be 5 and the puzzle would be broken. So those are not doublers. I'm going to mark non-doublers as green and doublers as red. Well, hold on. What's happening down here, I just realized? Because this has 4 cells in it already. So if we went up here, we'd go blah, 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 blah. That'd be 7 cells. That's not possible. So actually, down here, we also go right. We go up. And then we can't go up again, because that would be 7 cells. So we go right again. That gives us a little more path. And same idea here. These are 6 cells. So these are safe, because there is a doubler somewhere in these 6. Okay. That's kind of huge. Now this has 3 cells in it. So unfortunately, we don't know exactly how it moves. It could go up and get 6 cells that it's allowed, and then move out of the box. Or it could go right here. Don't know yet. But just right off the bat, we actually get a huge amount of paths to think about. Which is interesting. Let me read something really quick. In this experiment, dotted box borders divide the correct path into segments. Okay. So that means this segment is not the same as this segment up here, which is good. Because if it was, then we have to get 4 cells from here somehow. Actually, that would be fine, because it would be 6 cells in total. Well, anyway, that's not the case. These are different. This is a segment, and then this up here will be a segment. Okay. Now, what I'm thinking about is these 6 cell segments. Do they have to follow the example that I gave? Do they have to have all... Yeah. I think that the example I gave is actually the only way you can have 6 cells on the segment. Because yeah, you're going to have one doubler cell that's going to be kind of an extra cell there. And then you have the normal 5 cells of the rules of Nabla lines, in which if you have 5 cells on a single segment, they have to all be the odd digits. So what I'm claiming here is that these 6 cells contain all of the odd digits plus an even digit that is doubled, that is a 6 or an 8. Because if that even digit was doubled, but it was a 2, the value of it would be 4, and then it would clash with both 3 and 5. And if it was a doubled 4, the value of it would be 8, and it would clash with 7 and 9. So these 6 cells contain all the odd digits, plus... That's interesting, yeah. I am going to keep the coloring for if it's a doubler or not. But what I'm thinking now is I may want to mark what is an odd and what is an even cell. Okay, maybe I won't do that strictly, but I'll think about it. So these cells, well, like I said, 2 and 4 can't be here, even if they're doubled. So they will have to be here. And then the other digit here will be either the 6 or the 8, whatever is not used over here. So these are from 2, 4, 6, and 8, and they definitely contain 2 and 4. These are from 2, 4, 6, and 8. That can't be a 2 or a 4, because these cells contain 2 and 4. So that is definitely a 6 or an 8, and it is non-doubled. Okay. So now... Well, actually, that's all of the even digits in this column. That's fascinating. Wow. Yeah, this puzzle... This is 4 stars. But at least the beginning is flowing really nicely. Because now I'm going to claim these can't be doublers. Because if they were, like we said, they have to be doubled but the digit on them has to be even, and it can't be, because these are all the evens for this column. So these can't be doublers. They are safe, which means that we can treat it as a normal cell, and that black dot is a 3. Well, it's not a 4. This is fascinating. Yeah, it's not a 4, because like we said, all the even digits are taken. So this is a 3, which means that is a 6. None of those are 6s now. Let's see. Yeah, that's correct. Wow. That's fascinating. This puzzle's really cool so far. Well, now, what is this? Because that has to be on a black dot relationship with this 3. And this is actually what I was thinking about with doubler cells plus black dots, is that they're actually pretty restricted. Because, for example, you can't have a black dot with a doubler cell on one of those cells, in which the relationship that you have is a 3-6. Because normally, on black dots, you can't have a 3-6 pair. We just proved that right here. But I'm going to claim that this can't be a doubler, because if it was, what would it be? Well, either the value in the cell has to be 1.5, so the digit that we put here would be 0.75, which I'm going to tell you that's not a digit, or the value here has to be 6, and the digit we put here is 3, but that's not allowed by Sudoku. So this is not a doubler. This is safe, and it is a 6. It's the other 6 for this relationship right here. But now, what about this cell? This can't be as many things as you might think it can be. Because let's think about this. If this was an 8, then what's this? Well, either its value would have to be 16, so it would have to be an 8, which is impossible, or its value would have to be 4, so it'd either be a double 2 or a normal 4. Now, if this was a 4, its value would have to be 8 or 2, so it would have to be a normal 8, can't be a doubled 4. Or it would be a normal 2, or it would be a doubled 1. And if this was a 2, its value would have to be 4 or 1. So either it would have to be a normal 1, a normal 4, and it can't be a doubled 2. So either way, this is still from 1, 2, 4, and 8, which we don't know if it's doubled, but that is actually the same relationship that you would have in a normal Sudoku without these weird doubler rules. Also, another thing, there has to be a doubler in this column, so it is up there somewhere, which means all these cells are safe. Okay. Now it gets tougher, because now I don't know exactly what to do. The rest of the puzzle. Well, one thing I know is that eventually we're gonna cross here, aren't we? Yeah, we are, because we are on this portion of the grid right here, and this is a closed-off area, except for these 2 doors right here, and this is the one we enter through, so this has to be the one we exit through. So eventually we are gonna cross that. And then we can't be coming from down to cross that, so we're going to be coming from here. If we go down one more time, that is actually possible. That is 6 cells. If we do a diagonal, so I can't prove or disprove anything quite yet. I can mark a few cells that are impossible for me to reach, but I don't think that's super useful right now. Just by, like, logic. For example, you can't reach this cell in any way. Because this isn't at the end of the path, so you'd have to come here in some way, and it would have to exit in some way. But it can't, if you look at it, if you look at all the possibilities, you're stuck. You hit yourself. So these 2 cells are impossible to reach, but I don't think that's super useful anyway. Well, 6 is down there. I can mark that right off the bat. These are odd digits, which aren't 3, so they're 1, 5, 7, and 9. Is there a digit that must be one of these two? 8, right? 8 can't be. No, 8 could be there if this was a 4. 1 could be there if that was a 2, for example. 2 could be there if it was doubled and that was an 8. 4 could be there if that was a 2. Okay, no. I can't disprove any digit there. That's okay. These are 2, 4, and 8. Oh, these are 2, 4, and 8. So I actually know these digits. And the doubler here is the 6. So I should actually mark this somewhere. I don't know where I can do that. But I want to make sure that I don't double another 6. Because we know the doubler here is going to be a 6. Ah! So in fact, we know that the doubler here is an 8. Yeah. Yeah, okay. That's super useful, actually. Yeah, we know the doubler here is going to be an 8, because like we said, this has to have all of this segment here has to have all the odd digits, plus a doubler that's either a 6 or an 8. Well, it's not going to be a 6, because 1, the 6 is already here, and 2, the 6 is already placed in this box. So there is an 8 there, which means there's not an 8 here. This is a 2, 4 pair, which means that's not a 2 or a 4. This is now a 1 or an 8. Don't know which. If this is a 1, it's normal, so that's a 2. If this is an 8, oh, that's beautiful. That's beautiful. If that's an 8, then it is doubled, like we said, but then its value is 16. Well, 16 over 2 is not 2 or 4, so that can't be an 8. That is a 1. And that is a 2. And that is a 4. And that is safe. Oops. Which means the doubler isn't there. Which means those are safe. Which means the doubler here isn't there. Which puts the 6 there. Because like we said, the 6 has to be doubled. The 6 isn't there in that one. This is fascinating so far. So these are from 8, 5, 7, and 9. Okay, so now, what can these squares be? They can't be 1, 2, or 4, and they are safe, so we don't have to worry about doublers on them. And the only digits that can go on a black dot in general, if you're not talking about doublers or whatever, are 1, 2, 4, 8, 3, and 6. 1, 2, 4 are gone. 6 is gone, because 6 is over here. It's not in there. So these are a 3, 8 pair. Which means one of these is going to be 6, so that's not a 6. The other one's going to be a 4. So these are a 4, 6 pair. So it doesn't do too much. It puts a 3 in there. It puts nothing. These contain the 2. Oh, and it's right here. Can't be there. Silly me. And the other digit is an odd digit. And it's not a 1. Well, I knew that already, actually. 1 has to be up there, because it's not in any of these. So this is an odd digit that's not a 1 or a 3, because 3 is already taken. So this is a 5, 7, or 9. Not super useful. Trying to think if we can figure out which way the path goes, just with this. If the path goes this way, then that has to be an 8. That has to be a 4. Because that can't be a 3, because there's already 2 on the path. That would have to be a 4. for the black dot. Problem is I don't know if there's a doubler here, so I can't be sure of what's going on with that part of the path. Don't know yet. That's okay. We'll figure that part out in a bit. Maybe. Okay. Now. What? Now, okay. Now I'm gonna look at what I thought I was gonna look at immediately in this puzzle. By the way, how long is this recording? It's about 25 minutes, not too bad. I think I've done a good amount of puzzle for 25 minutes. I was gonna look at this. Because what I'm asking myself is, what the hell's going on here? What is this digit? What is this digit doing? Because what this is saying is that this digit somehow has 3 digits that are either half or 2 times it. I'm going to tell you, whatever digit I put there, there's only 2 digits that fit the description of half of it and 2 times it. So what I'm understanding is that there has to be a doubler in this. Yeah, okay, there has to be a doubler in that configuration. And I don't think... Yeah, it can't be the cell in the middle. Because if it was, then we still have the same problem. There's only 2 digits that are half or twice of its value. So that's a safe cell. And then one of these is definitely a doubler. Which means those are all safe cells. And the way that's going to work is if, for example, this is a 4, then this could be an 8, this could be a 2, or, sorry, that could be a 2, and that could be a doubled 1. So if these were safe, and that was a doubler, this would be correct. Because that dot works, 2, 4, that dot works, 2, 4, and that dot works, 4, 8. Now, what I'm also thinking is that that might be one of the only ways, or actually the only way to make that work, because that square can't be a 2. Yeah, I think I stumbled across the exact way that can work, because that square is safe, for starters, and it's not a 3, 6, or a 2. So, in general, it's a 1, 4, or 8. Do doublers frick with that? Actually, they do. So I can't say specifically that this is a 2, 4, 8. Wait, yes I can. Yes I can. Okay, here's one thing I forgot to say about doublers. Plus black dots. Usually on a black dot, you can't put a 5, a 7, or a 9. And I think that's pretty evident why. If you put a 5, then the other digit would have to be either a 10 or a 2.5. If you put a 7, the other digit would have to be a 14 or a 3.5. If you put a 9, then the other digit has to be an 18 or a 4.5. Now, do doublers fix that? No, they don't. Because if this was a 5, then you could say, oh, that could be a doubler. Well, it would be a double what? It would be a double 5. And that's just not allowed by Sudoku. You'd have 2 5s right next to each other. So doublers don't fix the fact that 5, 7s, and 9s can't be on black dots. That's still a general truth of black dots. So, now that I said that, yes, this can only be a 1, 4, or an 8. If it was a 1, how does this work? All of these have to have a value of 2. That's not possible. 1, because creating a value of 2 either requires a double 1 or a normal 2, and we already used up the 1, so that can't be a 1. If it was an 8, these all have to have the value of 16 or 4. They can't have the value of 16, because the only way of creating that is a doubled 8, and we've already used the 8. So you'd have to have 4 cells, or 3 cells, that have a value of 4, and that's also not possible, for the same reason. So this is a 4. And then 2 of these cells are going to be natural 2 and 8, and the other one's going to be a doubled 1. Well, the 2's right there, because the 2 can't be in any of these. And the 2 is natural, like we said. And these are doubled. One of them is a 1, and one of them is an 8. Now, we have the doubled for this row, so that's not doubled. That is a natural, which means it's not an 8. Because we know the 8 here is the one that's doubled. It's also not an 8 because the 8 is taken there. These are 5, 7, and 9, just by Sudoku. These are all safe. Does that tell us anything? Maybe. Ah! Okay, well, one thing I need to start writing down is the 1 is double here. So the 1 can't be doubled up there. So the doubler there is going to be 5, 7, or 9. Oh, by the way, these are safe. Because, like I said, we already have the doubler for this row. So yeah, I should be writing these down somewhere. I'm just going to do it on my notepad on my phone. So the doublers we've found are... I'm going to write them down by box. Just so I have an easier time differentiating them. So the one in box 1, we don't know yet. It's from 5, 7, and 9. The one in box 2 is definitely a 6. The one in box... or not box 2, sorry, that's box 4. Is definitely a 6. The one in box 7 is definitely a 8. And the one in box 9 is definitely a 1. So any doubler cells can't be 1, 6, or 8. Like, ever again. In this puzzle. Now, what I'm thinking of is, does that restrict the way that the line moves through this box in any way? I'm thinking, if the line enters through there, it's going to have to... That was... It's going to have to traverse this section here, in which it'll pick up at least 2 cells. Then it's going to have to come up here. I don't think there's too much of a problem with that. Okay, I don't think that's a useful way to think about it. We can't think about any of these X's yet, because they don't really align very well with digits we have. I can do a little bit of Sudoku. 2 is up there. If 2 is on the black dot, it could be doubled together with an 8. Or it could be normal together with a normal 1. Don't know yet. This black dot relationship might look weird, by the way, but it doesn't necessarily mean that there is a doubler in it. This could be all natural. This could be 2, 1, 1, 2. That works perfectly. So this crossing a box border, it looks weird, but it's not as weird as this one, which is why my brain gravitated to this one. 1 by Sudoku is also up there, which makes me think that this black dot does contain a 1, 2 pair. Can we get the third digit that's there, actually? Not quite. 4's down there by Sudoku. Okay. Okay. Well, what am I looking for now? I think I am going to have to think about this, unfortunately. Okay, so one thing I can say is that the digits here are 1, 2, or 8. Because like we said, no matter doublers, no matter anything, the digits on the black dot can only be 1, 2, 4, 6, or 8. They're not 4, 6, because the 4 and 6 is here. Sorry. 1, 2, 3, 4, 6, or 8. They're not 4, 6, and now they can't be a 3, because they don't pair up with anything. So these digits are definitely 1, 2, or 8. And now I'm thinking that they must have a 2. Yeah, they must have a 2, because if they were 1, 8, then no amount of doubling could make that black dot work. Doubled 1 would be a 2, 8 pair, which isn't correct. doubled 8 would be a 1/16 pair, which definitely isn't correct. So there's definitely a 2 in there, which means that's not a 2. So this is either a double 2 with an 8, or it's a double, or it's a normal 1 with a normal 2. Either way, these up here are also going to be from 1, 2, 4, and 8. Don't know exactly how yet. But they will be. One is natural here. So that can't be a 1. Because it's on the path. And there's a 2 already on the path. And that 1 is natural. So that's definitely not a 1. Since 1 is one of these two. Now I can't say that that's not a 1. Because again, these paths are different. Right? Let me make sure. Dotted box borders divide the correct path into segments, each of which must be a valid Navier line. I think I'm interpreting that correctly. I think I'm interpreting that this segment is completely different from this one. I'm pretty sure I'm interpreting that correctly. I hope. If the path goes like this, then that can't be a 1, and that would be forced to be a 1. Otherwise what? Well, okay, wait. If the path moved like this, what would happen? This would be forced to be an 8. That would be a 4. That would make that a 6, and that a 3. That doesn't really matter for this. Yeah, no, that's completely fine. What about the other way around? If that was a 3, and that was a 6, that was an 8, and that was a 4. No, those are all fine. Because even if this is doubled, it would be a doubled 5, 7, or 9, which gives us 10, 14, or 18. And those are completely fine together with the 8. So I don't think I can figure out what way Finks goes at the start here, unfortunately. If Finks goes... That might be interesting. If Finks goes up, she must go through these two cells, and then they're on the same... Yeah, okay, there we go. If Finks goes up here, she must go through these two cells, and they're natural. Well, what are they? They can't be 5s or 7s, so they'd both be 9s, because that's 6. So Finks does not go up, she goes right. She enters this box now, which is interesting. How's that going to resolve itself? Well, this is natural. So there's actually a lot of things it can't be. It can't be a 1, a 2, a 3, a 4, or a 5. So it's a 6, 7, 8, or 9. It can't be an 8, because 8 is taken in this box. So it's a 6, 7, or 9. And now what? Finks... okay, there we go. Finks will now have to get out of this little 2x3 box, so she'll have to go through there. And now what's that? That can't be a doubled 1. Never mind. That could be a doubled 1 if we did this path instead. Shit. Because then we'd have some number here, 8, 4, 2. And that's fine. But we do take that path, that's for sure. And then what I'm thinking is, can we go over here? Because the minimum way of getting there is through that. And then, what happens? We have 3 cells here. Yeah, this would be 6 cells. Which normally would be fine if all of the non-doubled cells were odd, but that's even. So that's not fun. So we don't go left here. We go up. Which tells us what? Not much, honestly. And by the way, that also doesn't work if we move like this. Basically, because there's like a wall of even digits here, we can't have 6 cells in this segment. That just doesn't work. Because even if this was 16, that would be a 2, so that makes 1 and 3 not placeable. And we still have to place 4 more digits. That's not going to work. Right? Yeah. No. Does it work? Shoot, have I been doing this wrong? Wait, I didn't think about this. If this was an 8, this was a 9. Now, what digits do we have left? We don't have 1, 2, 3. Well, we don't have 4. We have 5, 6, and 7. Yeah, you can't put 3 of those in here. I can't space that out any better. Yeah, okay. No, I was right. Yeah, I'm right. It's the same thing we proved before. I just forgot the proof. Like, if you discount the doubled cell, you still have 5 cells which you need to fill, and the only way to fill 5 cells in an Abra line is to make them all 5 digits. So, like I said, that's not going to happen. We're going to move like this. Now what? I don't know. This is hard. I don't want to ask for a hint. I just hope that I won't need one. I guess I can mark these. These are 3, 5, 6, 7, and 9. Those aren't 6s. That can't be a 3. Because either way, like I said, we're going to move through this wall of evens. And both 4 and 2 are adjacent to 3, so that can't be a 3. That's a 5, 7, or 9. Oh. For a second I thought we had a problem if that was a double 1. But I still don't think we do. Two, 3, 4. This is going to move through 4 cells. Which is much lower than the... Well, it's going to move through 4 cells minimum. Because it's going to take this one of these 2, that, and that. Which, yeah, that's much lower than the maximum that we said. So we're fine. For now. Unfortunately. If it moves like this, then that can't be a 5. But I don't know that it does. One of these is a natural 8, and one of them is a doubled 1. If we move through the natural 8, that's forced to be a 6. That's forced to be a 5. And then we can't move through the 4. So we have to move through the 2. Oh. Oh, we done it. Okay. Yeah, if this is a natural 8, then this is forced to be a 5, that's forced to be a 6. But they're on the same segment. That's not allowed on an Abra line, 5 and 6. So this is not the natural 8, this is the doubled 1. And that is the natural 8. And now we can't move through the natural 8, like we said. We are moving... Oh, we're moving through a doubled 1, so we can't go to the 2. We can't go through the natural 8, so we go directly to the 4. And now, because we're on a 4, this can't be a 5. It's a 7 or a 9. Which is decent. We're taking 2 and 4 right now. Which actually takes out a bunch of stuff. It takes out 1, 2, 3, 4, and 5. So any cells on this path have to be from 6, 7, and 9. What I'm thinking is, can we move like that? Probably not, but I don't know why yet. Because I'm thinking, if we move like that, then these constitute a 6, 7, 9. Oh, they constitute a 6, 7, 9 triple. And then 6 and 7 are going to be on the path, which is impossible. So no, we don't move like that. We move directly. Oops. We move directly here. And that is this segment. Done. Yeah. So then, yeah. Yeah. Don't know anything else other than that. Okay. What can we do then? These are from 6, 5, 7, and 9, and the 6 is doubled. There can't be an even digit here. Yeah, I know that. The 8 is down here. We already knew that. My bad. 2, 4, 6 are up there. Doubled 1 is there. Whatever the 1 is here, it's not doubled. If the 1 is there, then the path goes up. If the 1 is there, then nothing. Doesn't mean anything. 1 is fine with 3 or 8. Problem is, these X's could also have doublers on them. Oh, sorry, that's a doubler, which means those are not doublers. Should keep an eye on marking those. Which, yeah, that means these are not doublers, so they're normal. So they're not a 1-9 pair. They could be 2, 8, 3, 7, or 4, 6. Either way, they're definitely normal cells. They took their normal pills. That's not a 7 because it's not a black die, so that's not a 3. I'm sorry. Why did I say that? Jeez, I'm sorry. If these are a 3 or a 6, then that has to be a 3 or a 6. And that's a 7 or a 4. That's fine. Nothing wrong with that. This is on a black dot, and 2 and 4 are looking at it, so it's a 1, 8, 3 or 6. I don't think I can actually remove anything from there. Well, I can remove 8. Because how can this ever double or be normal and be a 4? Can't. So that's not an 8, that's not a 2. 6, 3 works fine, like we said. 4 with a doubled 1, 2 with a normal 1, 4 with a normal 8. Doubled, well, no, that can't be doubled. 4 with a normal 8 does work. That would be a 2. Okay. Don't know yet. What can I say? I can say what that is. That's not super useful, but that is a 1, 2, 4, a 3 or 6. Oh, this might be more useful. This is a 1, 2, 8, or a 3. It can be a 3, because this can be a 6. 3 is one of those 3 in that row. There's definitely a 2 in there, so that can't be a 2, like I said. It's a 1, 8, a 3, or... it's a 1, 8, or a 3. if that's a 1 or 8, this is from 1, 2, 4, and 8, and that's all of those cells. That's a quadruple there. Don't know if that's right, unfortunately. Oh, I'm recording. 50 minutes? This has flown by. My gosh. Yeah, this is gonna be a long video. I knew it would be. But, wow. 50 minutes already? That's crazy. That is actually crazy. I guess, yeah, the cupcake could be doubled. There's nothing stopping it. I guess I should mark that. The cupcake is either 1, 8, 3, or 6. Because of that 2, 4. That is 2, 4, 8, 3, or 6. That is 1, 3, 6, or 8. Which actually gets us pretty close to a quadruple there. That is 1, 2, 4, 3, or 6. I guess I might as well mark these. Oh, that can't be a 2. Okay. It's 1, 4, 3, or 6. Can that be a 1? No. Because you can't get a value of 2 here. Can't be a 1. That can't be an 8. Can that be a 1? No, because you can't get a value of 2 there. So that can't be a 1. This could be a 3, 6 pair or a 4, 8 pair. In which case it... This can't have a doubler in it, can it? Yeah, because if it did, everything would break. Because if it was doubled and it was a 3, 6 pair, then you would either have a 6 and a 6, or a 3 and a 12, and that doesn't work. If it was doubled and it was the 4, 8 pair, you'd have 8, 8, or 4, 16. So these actually can't be doubled, weirdly enough. That is normal. Wow. That's surprising. That can't be an 8 either, because you can't get a value of 4 here. Fascinating. Okay. That can be a 1, because that can be a 2. 3, 6 works, and 4, 8 works. Okay. If I could get rid of 1, 2, we'd actually have a quadruple there, which would be nice. But I can't do that. I don't think. Oh, 1 can't be doubled. I just realized. Neither can 8, 6, or... Yeah, those are the only numbers I have so far. Okay, yeah, so I'm pretty sure the doubler is not there. I think that logic was sound. Just make sure I didn't fuck it up yet. Okay. I'm thinking, can that be a doubler? I don't think it can. Because it can't be a doubled 1. It can't be a double 3 or 6, because then this black dot would break, and it can't be a doubled 8, because then it'd be 16, and it can't put anything there that works. So I actually think that can't be doubled either. That is weird. Because yeah, it can't be a doubled 1. If it could be a doubled 1, then 1, 4 would work. But it can't. Because doubled 1 is already there. So I think that's safe as well, weirdly enough. It's weird. The black dots are like kind of making it impossible for cells to be doubler. And I thought they would do the exact opposite. I thought it would be really common to have doublers on the black dots. But it's really not. Okay. Now what can we do with that? It's a great question. I don't know yet. Can this be doubled? I think for the exact same reason, no. Yeah, exact same idea is there, so that can't be doubled either. Wow. Okay. Weird. Very weird. Did not think that would happen. Okay, well, doubler is one of those 3 cells. If I get rid of that one, that would be really nice. Or these two. What was in one of these 3 cells? Shoot. Okay. Let's see. What can we do here? I am confused. Can I prove that there has to be a doubler, like, somewhere on this line? I don't know. Worst part is I don't even know how this line moves, because I want to say that it's going to connect to here somehow, but it's not necessarily the case. It could go here, and then, like, there. Oh, wait, can it? Shoot. Let's do this. I just realized there's a X here. Darn, that does work. How did that work? Wow, that's weird. It can... This line can move here, because it would have to go there. That's 4 cells. And then it can either move down, in which case that's the 5 cells it's allowed. Well, that's 5 of the 6 cells it's allowed. Or it can even move up, in which case that is the 5 cells it's allowed. It can move down, because those are all non-adjacent. And then it can go over here and just continue its path however it wants. Oh, but it can't. Can it? Oh, it could do that. So weird. It can... I think that is possible. Weirdly enough. I think that path is actually possible. I don't see something strictly wrong with that path, and that is really annoying. Because what we can't do, and I was thinking about, we can't do that, because that definitely has a 1 and a 2 in it. Well, but we don't know... We don't even know if the 2 is doubled. So yeah, I don't know. I am kind of stuck, honestly. This line either escapes through down here, or up here. If it escapes through up there, then this whole box is unused by the line, which I'm guessing is not going to be the case. But how do we prove that? I don't know. These cells are all out of bounds, aren't they? Yeah, they are. It's kind of obvious. Don't really need to mark that. I don't think. Okay. I don't know. I don't know where to look right now. It's a problem. If 3 isn't there, then 3 is there. If 3 is in one of those, then 3 is in there. Which would mean there's a 3 and a 4 in this part. Okay, that might be interesting. If 3 is in one of these, then there is a 3 in there by Sudoku. But that means there's a 3 and a 4 there. Which would mean that one of them has to be doubled. And it couldn't be 3, because there's already a 6 on the line. So it'd have to be a doubled 4. And then what would we have? We'd have 3 on the line, 6 on the line, and a value of 8. So we couldn't put 9, 8, 7, 6, 5, 4, 3, or 2. Wait, that's huge. Is that right? Oh my god, I think that's right. Hold on. We know there's a 4 there by Sudoku. Now, if 3 is there by Sudoku, there's also a 3 here. That can't be possible without a doubler, because 3 and 4 are adjacent. So the 4 would have to be doubled, because the 3 can't be, because there's already a 6 there. So the values we have there, let me just draw it here. The values we have there would be already 3, 4, or not 4, sorry, 3, 6, and 8. 3, 6, and 8. So what values are unallowed by that? And also, we already used our doubler, so we don't have to think about that anymore. 9 is not allowed, 8, 7, 6, 5, 4, 3, and 2. So the only value that's allowed for the remaining cell in here is 1. But we know 1's up there. 1's not down here. By Sudoku, 1's not down here. So I think neither of those can be a 3. And that is our 3. Huge! That's huge! Because then now that is a 3. And now, that is a 6. By black dot magic. Because this can't be doubled. Because if it was, you'd have a value of 6, and you have to put either 12 or 3 here. But by Sudoku, you can't put a 3 there. So this is safe. And then, this can't be doubled, because it would have to have a digit that is 3. And you can't do that. So this has to be a normal 6. Like we said, a 3-6 pair has to be all safe. That's not a 6, which means it's actually safe. 6 is up there now. That's not a 3, which means that's not a 6. That is actually huge. 5, 7, 9 puts a 6 there. Now that's not a 6, that's not a 3, that's not a 3, so that's not a 6. This is huge. That was a really good find, wow. Okay, now what I'm thinking. Wait, 5, 7, 9, that's an 8. Oh, that's huge, because now that is a 1, 2. And we said the 8 is doubled, so the 8 right here, is doubled. This is safe. And it's not an 8, which means those are safe. They are a 1, 2 pair, and that just works on the black dot. They are safe, which means they're not doubled. The doubler's down there, by the way. Which I'm thinking means neither of these can be an 8. Because if they were, then they'd have to connect to a 1 or a 2 below them, and that's just not possible. So neither of those can be an 8 now. They are 1, 2, or 4. These could all be safe, and it's just 1, 2, 2, 1, or 1, 2, 2, 1. Or one of these could be a 4. Well, could it? If one of these was a 4, we could do something like 4, 2, 2, 1. That actually works. Without even a doubler. Yeah, that actually works. Wow. What I'm trying to understand here is it even possible to have a doubler here? It's not possible for the 4 to be doubled. It's not possible for the 1 to be doubled. So if you had a doubler here, it would have to be a double 2. Which would then have a value of 4. So you'd have to go together with an 8 or a 2 below it. But it can't go together with a 2 below it, because that's not allowed by Sudoku. So these are actually safe. Which means in this row, these are the doublers. Which means those are not doubled. This is really cool. Do we know what the doubler cell is here now? I don't think we do, unfortunately. Well, let's think about what these digits can even be. They can't be 1, 2, 3. It could be 4, 5, 7, 8, or 9. If 5 or 7 was here, it would have to be doubled, so it doesn't clash with the 6. But if they're not, then they're here. Which means 9 is here. Okay, yeah. Wow, this is incredible logic. Okay. If both 5 and 7 are in this line, 5 and 7 can't both be in this line. Because then only one of them could be doubled, and the other one would clash with 6. Now, if there is a 5 or a 7 in this line, then it has to be doubled, so it doesn't clash with the 6. Hold on. Yeah. But now, the third option is there isn't any, and the 5 and 7 are over here. But that means there's a 9 here. But then, there'd also have to be an 8 in here. There is an 8 in here, just by Sudoku, actually. And so the 9 and 8 don't clash. One of them would have to be doubled. Shoot. And it would have to be the 9, because it can't be the 8. I didn't think of the possibility of the 9 being doubled, actually. Yeah. So the doubled cell here is a 5, 7, or 9. It's actually interesting, because that's the same idea as up here. So in box 8, the doubled cell is a 5, 7, or 9. If it's a 9, if there's a 9 there, don't know. If it's a 9, then the 8 has to be... Sorry, if it's a 9, then it has to be doubled, because the 8 can't be doubled. If it's a 5 or 7, then it has to be doubled. So the 4 here is definitely safe, is what we're finding out. And the 8 is safe. And then whatever digit's left is doubled. And whatever digit that is, it just works. 4, 6, 8, and 10, 4, 6, 8, and 14, 4, 6, 8, and 18. Those all work for nabler line purposes. Oh, there's a 6 there, so that can't be a 9. That's a 9. So that can't be a 7, sorry, that's a 9. Okay. Now what can we do? There was a lot of progress really quickly, but I think it's gonna slow down a bit here for a bit. 6 has to be a there by Sudoku. Still don't have that many digits in the puzzle, unfortunately. 2 and 4 are there. Oh, 2, 4, and 8 are there, so I can get rid of those markings. Must there be a 2 in there? Yeah, because if these are safe, right? If there were 1, 4, then they wouldn't work. So there must be a 2 in there, which means that's not a 2. Small victory, but sure. Because these are the 4, 2, 2, 1, 4, 2, 2, 1, or 1, 2, 2, 1, 1, 2, 2, 1. Unfortunately, these can be for anything. Those can't be 2s. It can't be 1, 6, or 8. What can they be? They can be 3, 4, 5, 7, and 9. That can't be 4. Wait, sorry. I was thinking that both of these were. By the way, those are not green. I don't know why I colored them green. Thank you. I was thinking that both of these were doublers for some reason. It's definitely not the case. What can I do here? If this is both safe cells, then it's not a 3-7 pair, it's not a 4-6, so it'd be a 1-9 or a 2-8. Don't know how to disprove that. This, I could try to mark that. That's a 1, 2, 4, or 3. It's not a 6 or an 8. So this is a 1, 2, 4, 8. It can't be a 6, so that's actually not a 3. So these are from 1, 2, 4, 8. That's from 1, 2, 4, 8. Okay, well, same idea. Can that be an 8? Yeah, because that could be a 4, and it could be natural. Actually, no, these all work. These all work. What am I missing here? Don't Don't know yet. Still have a lot of paths to draw. I'm trying to think how that's gonna work. Well, now it's become kind of hard to traverse this section of the grid, because there's a 3 right there. And we can't touch whatever 2 is close to it, so we definitely can't do that. We could do that if we then move directly upwards. Don't know. Oh, I don't want to turn off this recording. I've been here for like an hour, 10 minutes. That's already a pretty long recording, I'll tell you. This is on an X. Oh, at some point I deleted one of those digits here, so this should have a digit deleter as well. 64462. Yeah, this can't have a 7. It's 4, 6, or 8. 2, 4, or 6. 2, 4, or 6. Those are all even digits. Is that important? Not really. Maybe. Maybe. Struggling to see how this resolves, to be honest. These are odd digits. I know that much. 6 is in there. 5, 7, or 9 is doubled here. The heck, man. Okay. Can I somehow disprove this as doubled? I don't think I can, because this could be a doubled 1 with a 4 there. That's fine. Double 2 with the... Actually, no. Yeah, this can't be... Shoot, I don't think this can be doubled. Because it can't be a doubled 1, because there's already a doubled 1 there. If it's a double 2, then its value is 4. But then the only cell that goes together with it here is a 2. And you'd have 2 2s in the same row. If it's a doubled 4, then its value is 8. But the only cell that goes together with it here is 4. And you have 2 4s. If it's a doubled 8, then its value is 16, and nothing goes together with that. So this is safe. Okay. One more safe cell under our belt. Well, now can we think about that cell? Because if that's safe, that's either a 9, an 8, or a 2. It actually can't be a 6. But if that's not safe, then its value has to be one of those. Its value can't be 9, because 9 is odd, and no digit times 2 is 9. Its value could be 8 if it was a 4, actually. So doubled 4 with a 2 would work. Double 3 with a 4 wouldn't, because 3 is taken. And doubled 1 with a 2 wouldn't work, because 1 is taken. So this is from... Wait, can this ever be a 4 then? No. Because it would require either 6 below it or a double 3, so this actually can't be a 4. Which doesn't mean much, but it's something. Okay, so what are the options here? If this is natural, it's a 9, an 8, or a 2. If it's doubled, then its value is 9, 8, or 2, so it'd have to be a 4, with this being a 2. So this is from 2, 4, 8, or 9. Unfortunately. Because yeah, 4 hasn't been doubled anywhere. Only 1, 6, and 8 that we know so far. What can these be at this point? These can be 1, they can't be 2, 3, 4, 5, can't be 6, 7, 8, 9. That can't be a 4. That can't be an 8. It's not very useful. These are 2 and 4. That's an 8. These are 2 and 4. These are 1, 2. These are a 1, 2 pair. Nothing. Well, if they're a 1, 2 pair, no. If actually, if they're 4, 8 pair, if that's an 8, then that has to be a 4, and that has to be a 2. There's a 4, 8 pair there. Oh, sorry, 2 is taken in this box. That can't be a 2. My bad. This is a 1 or a 4, which means that can't be a 1. That's a 2 or a 4. It's a 1 or 8, my bad. Which means, actually, since that can't be a 2, this can't be a doubled 4 or an 8. So it's natural. There we go. Okay, a little more progress. The doubled cell is now one of those 4. This is natural. Those 2 cells work fine with each other on that path. But they are even. They are both even. Which I think means now that this path can't go down. Because it has 2 evens on it. Is that right? Hold on. If I make these as far apart as possible, then they would be 2 and 8. And the numbers that erases from possibility are 1, 2, 3, 9, 8, and 7. Well, okay. Just barely. Well. No. Okay, wait. That's huge, I think? No. It's not quite huge. But it's big. No, wait, it is huge. It is huge. It is huge. Yeah, it's huge. Let me remake that. So, if we think about not what it erases, but what's left, it's 4, 5, and 6. And if we move down, then we have to reach... Oh, shoot. Okay, no, hold on. Let me think about it from the other path. If this connects here directly, then it must cross at least 2 more cells. It must go like that, like that, like that. And then you have 5 cells. Or you have 5 cells to fill without doublers, but only 3 numbers. Well, not 5 cells. You have 3 more cells to fill with only these numbers. And you can't do that. You can get 4 and 6, but then the other cell is impossible. So this doesn't work. So that doesn't connect there, which means it connects here. And then that's going to move left. And now this can't move down because it would get stuck. If it moves left, then that has to be a 1, and then it must move up immediately. Or it can move up, in which case it would have to follow this path. That couldn't be a 1, 2 pair. Or sorry, that couldn't be a... That could be anything, actually. That could be a 1, 9 or an 8, 2. That doesn't matter. Okay, but we got a little more of the path. Get rid of those. Got a bit more to think about. That cell's alone, so it doesn't matter for the path requirements. This part of the path, though, must cross at least 3 cells. Well, okay, now this can't move down, because it would either connect here, which would make this path unconnectable, or connect there, which would make this path unconnectable. So this doesn't move down, this moves left. Which means it doesn't move down, it moves like this at least. Which is 4 cells. One of them might be a doubler. If it moves up, then it definitely has a doubler in it. If it moves down, then that's 5 cells. Don't know. Don't know yet. But that's definitely how that path starts, at least. And now this part is going to connect to that part, somehow. This can't, like I said, this can't move directly left. It can either do that, Or that. Well, it can't do that anymore. Actually, it could never do that, because it would cross a red X. What was I thinking? It moves left. It can't move left again, because then it would hit a 2, definitely. So it moves up, which means this is not a 2. This is a 1. That's a 2. That's our 2 here. Makes a 9 here, a 1 there. Ooh, now we're getting somewhere. These aren't 9s. That is a 4. This must move there, because it's the only way it can move. This is an 8. Those aren't 8s. This can't go up now, because if it does, that's 6 cells. But then, like we said, all 5 of the normal cells would have to be odd, and those are definitely even. So this doesn't move up, this moves down, which means it moves left. It can't go down here because it would get stuck. So it moves up here, like that, and like that. And that... that's the, like, joke path that I drew before. Being like, oh, that might happen. Wouldn't it be crazy if that happened? Well, guess what? It happened. That's, wow. That's amazing. I love that. I actually love that. I actually really, really love that. That's huge. Okay, well, let's think about what these cells are. These are, 1, 2, these are 3, 5, 7, and 8. Well, I see the problem here already. 7 and 8 are too close together, so one of them has to be doubled. It's not the 8, it is the 7. So one of those are doubled, and it is the 7. So box 5's doubled cell is a 7. Which is actually huge. Because like we said, box 1 and box 8, their doubled cell was either a 5, 7, or 9. But now it can't be a 7 anymore. So they constitute a 5-9 pair. So the boxes that are left, 2, 3, and 6, have the other digits in them, which haven't been used yet and aren't 5 or 9. And they are 2, 3, and 4. So the doubled 2, 3, and 4 are in these boxes specifically. Okay. I don't exactly know what to say about that, but it's kind of huge, I think. It's large, for sure. It's definitely large. This is an amazing puzzle, I must say. This is another fucking banger of a puzzle. So the doubler here is a 5 or a 9. The doubler here is a 5 or a 9. What can I do with that? I don't think I can figure out how this works, unfortunately. Because if this is a doubled 5, the 9 has to go over there. If it's a doubled 9, then 5 has to go over there. Wait, sorry. This can't be a doubled 9, can it? It can. That would just mean that 5 and 7 have to go over there, because 5 and 7 can't go next to the 6. So either these are 5 and 7, or there's a doubled 5 in here, and there's a 9 in there. Which, yeah, that's literally all the possibilities that exist. Either these are 5, 7, or they have a 9. How insightful. The doubler here is 2, 3, or 4. It's not 2 or 4, so it's actually 3. So there is a 3 there. And bada bing bada boom, the doubler in box 6 is a 3, which means the doublers in box 2 and 3 are 2 and 4. So that can't be a doubler, because 2 and 4 are taken. That's safe, which means the doubler is in one of those, which means that's not a doubler, which means that is a doubler, and it is a 3. This puzzle's sick. This puzzle's sick, dude. Hold on, that's not a 3. That's not a 6 now. That's not a 3. That's not a 3, so that's not a 6. 2-4 pair means that's not a 4. 1-8 pair means that is a 6. That is a 3. That is not a 6. Wow. So the doubler here is either 2 or 4. Okay, can't prove which one it is quite yet. But that felt huge. And I'm pretty sure it was. Just have to finish it off now. I think we're close. I think we're close to finishing it off. These are kind of restricted. They are 5, 7, and 9. Yeah. Oh, that's interesting. That's very interesting, because that is an odd number right next to 2 even numbers, which makes it kind of restricted by Nabner line logic. Because if that was a 6, that would be forced to be a 9. If that was an 8, that would be forced to be a 5. So it actually can't be a 7. That's a 5 or a 9. Now, if it's a 5, that would be forced to be a 2. That's fine. 2, 5, 8. Or 9, 6. Both of those work. Okay. We have a 2-4 pair there, actually. I didn't notice that. Kind of weird. 2-4 pair there. I can mark these, maybe? These are 5, 6, 7. Well, they're not 6. Oh, they're not 6. Yeah, 6 is taken everywhere in this column except for exactly there. That is a 6, that is a 4, that's a 2, that's a 4, that's a 2, that's a 6, which is our doubler. That is not it. These aren't doublers anymore because of Sudoku. So they can't contain the 7. 7 is up there. That is a 2. Which puts it together with a 1. Put that together with an 8. These are not 8. These are 3-5 pair, which means these are a 7-8 pair. This is amazing. Holy shit, that's not a 3 anymore because it's a 3-5 pair. So that is a 3. Which means this is 5 or 9. These are 1, 2, 3, 4, 5, 6, 7. 1 and 7. That can't be a 5 because it's an Abner line. So that's a 9. That's a 5. That is not a 5. That's not a 9. These are 1, 7, and 5. It's not a 1. Okay. The value of that is 6. So whatever this is, if it's 5 or 7, it can't move there. So it's actually going to move into one of, whoops, it's going to move into one of these two. It can't move there, because then it can't move there or there, so it'd be forced to move here. But then 8 and 4 would both be on the line, and that couldn't be a 5 or a 7. So this moves here, which means it moves to 8, which means this is a 5. That's not a 5. 1, 7 pair puts a 5 here, 7 here, 5 here, 5 not there. We still don't know which one is doubled here. It's either 5 or 9. Here it's either 2 or... Oh, it's not 2. The doubler here is a 4. And in fact, these are a 4, 9 pair. So the doubler in box 3 is a 4, and the doubler in box 2 is a 2. So whatever digit is doubled here, it is a 2. Here, it's either 5 or 9. Here, it's either 5 or 9. But I'm not sure which one yet. Maybe I should know that already, but I don't. Hopefully I'll find that out soon. These are 7, 8. Let's see. The cupcake is a 1. We must get to the cupcake somehow. We must have a final move. It can't be that, because then the 2 and a 1 would be on the path. It could be that. Well, it can't be that, actually, because then there would be a 7, 8 and a 7, 8. So, well, no, but it could do something like this. Ah, okay. So it could be that, it could be this, and it could be that. It can't be this because of that wall there. Don't know. What do we got? Must be some way of finishing this up. Oh, this is not a 7, because this is going to connect there, eventually. And then 8 and 7 are adjacent, so that is a 1. That is a 7. That's a 1. This can't connect here, because of that 5, or here, so it must connect directly there. And our path is almost complete. Just need to figure out the last little bits here of logic. What can I do? What can I do to finish this off? This is close to cracking, but not quite there. One goes up here by Sudoku. Doesn't go there. 2 goes up there by Sudoku. Oh, 2 goes there by stuff. The 2 in box 2 is doubled, like we said. So this is doubled. Okay, and that has a value of 4, so that has to have a value of 6. And all these are safe. That is safe. So it's, the value in box 3 was 4, so that is a 9. The 4 goes up here, it is doubled. That is a doubler. These are safe. 1 can't go there. 7 can't go there. So 1, so wait. That is a 6, that is a 3. I think we're actually might be done. That is not a 9. Oh, barely. Okay, we're barely not done yet. But we're very close, I think. That is a 1 now. Yeah, we're very close to being done. That is given. That is a 3. That is a 5, 3. That's not a 5. Okay, we're close. We're close. Close. Oh, that can't be doubled anymore. Because of good old Sudoku. So that can't be a... If 5 or 9 is in this, it's doubled, I'm pretty sure. Is that correct? I think so. Because if 5... Yeah, if 5 can't be there and be natural, obviously. Okay, yeah, that can't be a 5. I don't think that can be a 7. Yeah, because either 5 or 9 is here, and then 7's gonna be up here. So that can't be a 7, that's a 4 or 8. So close. So close, dude. That is a 7, 8, or 9. We have a 1, 3 here. That's not very helpful. Oh, now the path... Okay, now Finks can't do this, because it would be... She would have a 2 and a 3. So she does go like this. That is a 5, 7, 9... triple. Oh, huge, dude. That can't be a doubled 5, because if it was, it would have a value of 10. But then one of these is a 9. So that is a doubled 9. That is a 7. That is a 5. That is a 7. None of those are 7s. None of those are 7s. And the doubler here is a 9, which means there is a 9 there, which means this is a 5. And this is a 9. And this is not a 5. That's not a 9. I think we're done. 1, 2, 3, 4, and 5 go up here. These are 7, 8, 9. That's not a 9. Oh, but, well, yeah, we're not done with the path yet. I forgot. Okay. Well, yeah, let's finish off the path then. This can't go up or like that, because this is a 7, so it goes left. This can't go like that or like that, so it goes left again. Oh, now what? Now what? Great question, dude. Now, what is a wonderful question? I think this has a hard time going left, actually. Because this has a value of 4. So it can't go up. Because it would hit either a 4 or 5. It would have to go... It can't go left, because there's an X there. Oh my god, that X actually came into play. So this can't go left, this goes up. And now, it can't go here or here. Because 6 would clash with the 5 and 7, and then 8 would clash with the 7, so it goes left. And now, it doesn't go down because it would get stuck, so it goes up. It doesn't go left because it would get stuck, so it goes right. And it goes right into the cupcake. That is the path. I'm pretty sure that is the path. So now we just have to figure out what breaks here. Am I missing something? Because I'm pretty sure that is the path that works. 5 works with both of those. 4 works with both of those. What is broken here? What did I break? I broke something. Oh no. Did I break something like a long time ago? I haven't been checking. Because I thought... Oh no, okay, it wasn't that long ago. Thank God. What did I break? I broke something. Ooh. I broke that? Oh. Did I actually do that? Yeah, I did that. Wow. I said it backwards. Yeah, I literally just said it backwards. The doubler here is a 9, so the doubler here is a 5, which means there's a 9 there. Yeah, I just said it backwards. My bad. Happens to the best of us. That's an 8, that's a 4, that's a 5, that's a 7, that's a 9. That is our doubler. Whoopsie. That is our doubler. That is normal. Which means that is not doubled. Which means that is doubled. And it is our 7. That's our 8. That's our 9. And then the path does do what I said. It goes left, then left. Then, well, let me mark these. These are 7 and 8. Oh. Wait a second. 1, 2, 3, 4, 5. Okay. Yeah, okay, we can't go left because we'd hit a 5 there. 4, 5 doesn't work, so we go up. Can't go right or up, so we go left. Then we go up. Then we go right. Then we go right. Okay, yeah. And then that's a 4. And I forgot to put these in. That is a 7, and that is a 9. Wow. That was really, really fun. That was an amazing puzzle. I am really mad that I got it slightly wrong at the very end. It was literally just a mishap of the brain. Wow. That was really fun, though. I really liked that. Experiment completed successfully. Cells visited 58, blackcurrants eaten 6, forbidden doors used 0. Just like everything else she has faced so far, Finks showed remarkable aptitude for understanding how the modifier cells affected the task at hand, realizing that 2 6-cell segments would be possible if they used 6 and 8 on doublers. Exactly. Her disinterest in the forbidden doors felt almost like a defiant taunt. Hell yeah. That was really, really fun. Again, I'm mad at myself that I just fumbled that ending there. But that was so elegant. The entire way through, that was so elegant. And this path is just beautiful. Look at that. It travels around like the entire grid. It goes all the way through. That's so cool. That is so cool. I really, really enjoyed that. That was so, so cool. Marty Sears, what a fucking legend. And with that, we've caught up to the Rat Run series. We've completed every puzzle that's out. I'm really proud of that. I'm really, really proud of that. That wasn't that bad, dude. That wasn't that bad, honestly. I can see why that's a 4-star. It definitely deserves 4-star. It took me 1 hour 40 minutes to beat. But that honestly wasn't horrible. Like, I could do that, right? I was basically progressing the entire way through. I didn't get stuck for too long on any one thing. It flowed just so well. It was constructed so well. It was really, really good. I loved that. Okay, what is our solution code? Digits in row 2 that are on the path. That's a lot of digits. 279153. 279153. And there we go. That's it. That's so cool. That is so cool. So yeah, if I go to Marty Sears' page now and publish puzzles, he's already published another one today. What? He's just... wow. And it's a 1-star actually. Wow. Huh. I'll do that in my own time. All of his rat room puzzles, we should have those all done. Yeah, all 10 of them. There we go. That's so cool. That's so cool. And obviously the one that came out yesterday as well. So cool, dude. I can't wait for more. I cannot wait for more. These are marvelous. These are beautiful. These are freaking... oh, these are amazing. I love them. There we go. That is... oh, such a beautiful grid. Holy shit. That's really cool. I'm really proud of that one. That is a good solve. I'm not gonna lie. It took me a while, but that is a pretty good solve. I actually want to... I don't want to brag or anything, but I do want to Google how long it took Simon from Cracking the Cryptic to solve that. It took him about... let me see, if I take out the intro stuff, it took him about 54 minutes. Okay, so yeah, I took about double the time, which is fair. I'm not a Sudoku expert. I'm just a girl that likes to play Sudoku. And honestly, double the time of Simon, that's a compliment. That's a compliment. That's good. That's not bad at all. Okay. Well, yeah, that's it for now. That was fun. That was amazing. I can't wait to be back for more Rat Run puzzles. That was amazing. Every single one of them was beautiful. It's built so well. I'm glad Finks got all those cupcakes. She deserves it. After all that, she deserved all the cupcakes. There we go. Okay. That's it. Good night.